Okay, the last thing that I wanted to go over in this module is actually not something that's in OLI. It'll come up later, but it is grounded in the idea of the mean and the standard deviation and will become really important to us later on. So I think we might as well talk about it as many times as we can. And that is the empirical rule. So the empirical rule gives us a way to define or to quantify how the data is distributed in a bell-shaped distribution. So think of this like a histogram. Our data is along the horizontal axis. So this is where the x values are, right? Each piece of data is an x value. What are all these symbols in here? Well, they're the mean and the standard deviation. They're things we've already been talking about, but they're the symbols for population data. So this is the Greek letter mu. It's a lowercase mu, and this stands for a population mean. Remember that we used x bar to stand for a sample mean, but this is the mean of a population. And this is a lowercase sigma. Remember that our capital sigma told us to find a sum or add things together, but this is a lowercase sigma, and this stands for our population standard deviation. We used S to stand for sample standard deviation, but this is population standard deviation. So if we take a look at what's going on here, here's the mean at the center of our distribution. And that comes from our Archimedes principle, right? The balancing point is going to be right in the center if we have a symmetric distribution. From there, we're counting out. Plus sigma means +1 standard deviation, minus sigma is -1 standard deviation. So we're given this is the amount of data that we will find within 1 standard deviation of the mean, 68% of our data. And because it's symmetric, split that in half, and it's 34% on each side, again, within that 1 standard deviation. If I move out to 2 standard deviations, sigma plus 2 sigma, mu plus 2 sigma, 2 standard deviations to the left, mu minus 2 sigma, that will encompass 95% of our data will fall within that range. Now, where did these 13.5s come from? Well, it's a total of 95% of our data. 68% was already within 1 standard deviation. So 95 minus 68 leaves 27% of the data to be split in each side. And that's where these 13.5s come from. So if we took the 34 plus the 13.5, we would end up with 95% of our data, but divided in 2 because it's just on one side. And if we bump up to 3 standard deviations outside of the mean, then we will catch 99.7% of our data. So you can see how there really is almost no data outside of 3 standard deviations from the mean in a bell-shaped distribution. So there's our layout. Let's say we had a data set where the mean, the population mean mu, happened to be 20, and the standard deviation sigma happened to be 3. Well, then that means that right at the center of our distribution would be this value 20. And then normally when we're Graphing bell-shaped distributions in keeping with this empirical, recount out 1, 2, 3 standard deviations to either side. And remember that my standard deviation is the value 3. So 1 standard deviation away will be at 23. 2 standard deviations away is at 26. 3 standard deviations away is 29. And then if I go back the other way, 1 standard deviation back is 17. Subtract another 3, we're at 14. Subtract another 3, we're at 11. So, oh, well, that's not a very good bell-shaped distribution, but you get the idea. And we would then know that 68% of all our data is within the interval from 17 to 23, because that's 1 standard deviation on either side. 95% of my data would be in the interval from 14 to 26, and 99.7% of all my data would be in the interval from 11 to 29. All right, you're going to have plenty more time to practice with the empirical rule. I just wanted to introduce it here, have us start getting used to this bell curve. It really is the most important distribution in statistics.